Who doesn't love garlic? It's found in the guac you love from Chipotle, garlic bread, and if you're a true lover of garlic, there's a garlic festival in California where you can even find garlic ice cream. But garlic isn't just a delicious food flavor. Crushed garlic contains ajoene, a molecule that can act as an antioxidant, potentially help anti-proliferation of cancer cells, and halt microbial growth, among other possible uses. You must be wondering, how can an ordinary ingredient have such large chemical and medical implications on society?
To start us off, let's take a look at the molecule pictured here. After you crush a clove of garlic, this molecule called Haviland is released, and it isn't until the garlic is combined with oil that it becomes our molecule of interest, ajoene. Although this may look like just a jumble of lines and letters, each marking notates a unique functional group that gives rise to some of the properties that make each molecule so unique and able to react in different ways. One of the biggest contributors to ajoene's many uses are the S groups along the molecule. Ajoene contains both sulfoxide and disulfide functional groups. Sulfur is a large atom that can interact in ways with other smaller atoms to make them both more stable and help calm down any biological abnormalities.
You have most likely heard the word antioxidant highlighted in food commercials or on labels at your local grocery store. Well, the purpose of an antioxidant is found in its name. It works against oxidation. Oxidation can result in free radicals. These free radicals are often released as a byproduct of natural processes in the body, such as breaking down waste products or making energy. Free radicals, usually derived from oxygen, nitrogen, and sulfur molecules, are atoms, molecules, or ions with unpaired electrons. However, molecules prefer to have an even number of electrons, so each electron has a pair and is happy. If one magnet is unpaired, it becomes reactive and will desperately try to search for other magnets to pair with, even if the other magnet is already paired. These free radicals try to achieve stability by stealing electrons from nearby molecules, leading to chain reactions which are potentially harmful to cells. Antioxidants can stop these chain reactions from proceeding by accepting or donating electrons to make the free radicals stable. The body usually has natural forms of defense from the immune system to escort these reactive molecules away from potentially harming normal molecules and even redirect them to attack foreign molecules that could potentially harm the body. However, if they accumulate, they can age the immune system or ruin normal bodily functions.
Ajoene in particular works as an antioxidant by preventing superoxide from being released. Luckily, the sulfur attached to the O, or oxygen, in ajoene has a large positive charge compared to the other two sulfur atoms. This means it can donate its lone pair to the radical. It's less reactive since the molecule is so long, and S is large enough that the electrons are spaced in a favorable way that calms down the uneven number. In addition, hydrogen atoms bonded to the central double-bonded carbon atoms have the greatest positive excess charge compared to the other hydrogen atoms in the molecule. These hydrogen atoms are more likely to be used first in a proton transfer reaction, which can also contribute to ajoene's antioxidant properties.
As you can see, balancing reactivities of molecules is an important way to make sure nothing in the body goes too crazy and messes up normal functions. Because of this, the sulfur group plays a role in why ajoene is used as a cancer treatment, and other treatments also include active ingredients concerning sulfur groups. Both the sulfoxide and vinyl disulfide have been tested.
Cancer cells have grown much past what the body is normally capable of handling, and ajoene can also help combat the spread. They can slow down the growth or create a signal to the cell to initiate apoptosis, or self-elimination. They do this by targeting the way the proteins responsible for the cell's function and shape are folded. There are 4 main steps in the creation of proteins, and ajoene plays the biggest role in disrupting the tertiary and quaternary structures, as these connections rely on particular arrangement of sulfur bridges.
When the cell notices the abnormal folding of some of these essential structures, it will realize that it needs to start the signal for apoptosis. Since these accumulating misfolds can hinder cell function in a way that simply being bloated is hard to notice, this slows the rate of cancer proliferation and speeds up the rate of remission.
Isn't it fascinating how something so simple can have many interesting uses? Believe it or not, lots of the molecules that shape our world today came from ordinary things that we take for granted in everyday life.
Traditional medicine exemplifies this phenomenon by using regular herbs or plants that are easy to access to treat a wide range of ailments. There are discoveries to be found everywhere, and the role of science is to pinpoint the causes and effects of active ingredients to improve overall quality of life and help educate the world about safety and discovery.